Okay, welcome people of the free seminar. This week we have Aaron Kettner, who is a local here in Prague, and he's going to give us an introduction to group actions and ergodicity. Yes.
Thank you, Thomas. So the goal is to introduce some basic notions that probably Akshara will use in his talk, and then talk a little bit about invariant measures to get you into the mindset of thinking about dynamics. So I will assume some measure theory, and I will probably go through these first things rather quickly, but of course interrupt me at any point if something is not clear. So the first definition is that of a Borel probability measure. A Borel probability measure is a probability measure, meaning that the whole space has measure 1, let's say mu, the Borel sigma algebra of a topological space S. So I'm assuming that everybody knows what a sigma algebra is, and I'm assuming that everybody knows what a measure is. The Borel sigma algebra of a topological space is the sigma algebra generated by the open sets. And then, you take a measure on the sigma algebra, and you want it to be a Borel, you want it to be a probability measure, meaning that X has measure 1. Okay. And it is called regular. For each Borel set A, so each set in the Borel sigma algebra, one has that the measure of A can be written as the supremum over the measures of sets K, where K is a subset of A that is compact. And at the same time, you can also write it as an infimum of the measures of sets U, where A is contained in U, which is open. I think commonly this first equality would be called inner regularity, because you can approximate your set from the inside, and this is called outer regularity because you can approximate it from the outside. And I guess it's not hard to imagine how that could be useful, because it tells you somehow how your measure interacts with the topology of the space. Right. The next definition will be that of a group action. So throughout the talk, and I think also throughout Akshara's talk, G is a discrete countable group. And then an action of G on a set X is a map alpha from X times G to X, which we write as, we send X and G to alpha G of X, such that alpha G applied to alpha H of X is equal to alpha GH of X, and alpha E, where E is the identity in the group of X is equal to X. So this should be for all GH in G. And note in particular that because of these two conditions, that alpha G is injective, is bijective. All G in G, and the inverse of alpha G is given by alpha G inverse. And now, of course, we don't want to look at we don't only want to look at actions on sets. We want to equip our sets with some extra structure. So, for example, X could be a topological space. And in this case, we want this map to be continuous. So if X is a topological space, then we call alpha a continuous action. If alpha as a map from G times X to X is continuous. Where G just has the discrete topology, because we assume it to be a discrete group. And the other important case is if this X is a measure space, so equipped with some measure. Then we call alpha measure preserving. Okay. If for all G and G, the measure of and all measurable sets, the measure of alpha G of A equals to of A. Right, so moving sets around using the action does not change their measure. Okay. Anything so far? So, as an example, let's take G to be the integers, and take X to be a doesn't matter. So take G to be the integers, then any action of the integers on some set or space or topological space or measure space necessarily is of the form alpha k of X equals T of k of X for T whatever is the right notion of isomorphism in the category you're working in. So I'm going to write a homeomorphism if you're working with, if X is a topological space, right? So, if you have an action by the integers, that is necessarily induced by a single transformation. And this is sort of the historical example. This is how the whole field of ergodic theory started, because this comes from physics. So you would think of X as being your phase space, this space of states of your physical system, and you would think of T as a time evolution. Of course, a discrete evolution. Usually we think of time as being continuous, but here you take these snapshots. So let's say you have some particle moving in space, or you have a gas in a box, and every 1 second you check what state your system is in. And this sort of, this provides you with the way of thinking for these group actions, at least in this context. So we want to think of them as dynamical systems, as time evolutions somehow. So you could start with some point X, and then you apply T, and you get to Tx, that's the next time step, and then you do this again, and so on. You sort of evolve in time by applying t again and again. Okay.
And about the definition of better resolving. Good way saying the map from X equal G to X is little.
No, because it's not just, you're not just asking for measurability, right? You're really asking for the measure to be preserved, in the sense that, like, applying the map does not change the measure, which is much stronger than.
Like, well, if we also give a action as a map from G to directions from X to X. Whatever.
But I'm not sure if I get the question. What's
so here in because the measure X probably would be different from the measure X.
Sorry, I'm not sure what the question is exactly. Not sure if I understand. So, I mean, you do need this map to be measurable. I guess that's like implicitly in the hypothesis.
Even simply asking that X cross G to X is
Yes, because measurable just means that three images of measurable sets are measurable again, right? You are not, when you define measurability, you don't need a measure, first of all. You only need a space equipped with a sigma algebra. So somehow this thing is really much, much stronger, that you're asking the measure to be the same after applying the map.
Oh yeah, maybe later.
Okay. But thanks. Good. Okay. And now, so all of this was originally in thermodynamics, and there it was discovered that a very important property of an action is to sort of see all of the space. So whether the question is, if you have some point and you start and then you apply your sort of time evolution, the question is, do you eventually get to see all of the space, or do you stay confined in some particular region? And that leads us to the definition of ergodicity. So if you take an action, which is often written like this, an action on a topological space X, with a Barré probability measure. Then we call alpha ergodic if the following holds. If you have a measurable subset A of X, which is invariant under the action, so alpha G of A is equal to A for all G and G, then that set must have measure either 0 or 1. So in a measure theoretic sense, it needs to be either nothing or everything. And that sort of translates into the thing that I said earlier. So what we're asking is, okay, if I have a set A, right, and now if this condition is fulfilled, if I take a point from A and I apply the action, I'm always going to stay in A, right? Like this orbit is entirely going to be within A. And ergodicity says that if that happens, the space, the subset needs to be either the whole space or basically nothing. Which sort of you could think of as orbits seeing the entire space when you move them around. Okay, so this is a very important property because it also means that, I mean, it's also the right notion of irreducibility in this context, because if you had such a set that is invariant under the action, you could restrict the action to it, and then you take the complement, and then you have sort of divided your action into this part A and in the complement, right? So you have, yeah, sort of reduce the system in a non-trivial way. And ergodicity means exactly that cannot happen. These are like the irreducible objects in your category or whatever. Yeah.
So this happens when A need not be the entirety of X or nothing. It's measured by.
Yeah, exactly. Yeah, so everything is just up to up to having measure 0 or 1.
The same sets for sets which are medical sets which are exactly invariant, not just that their image lies again within the set.
But that should be the same in this case because it's everything's invertible, right? So if I just, I mean, it's a very good question, but if you just had this for all G and G, then in particular, you also have it for G inverse, right? And then you just apply alpha G to both, and then you get that. Yeah. Yeah, no, but very good question. So I'm glossing over a bunch of things here, which I can do because we are only talking about invertible actions. If you talked about non-invertible things, you would have to be more careful. So yeah, you would maybe only want this to be contained, and then somewhere else with the measure preservingness, you would want to take, so here, if your alpha G was not actually a bijection, you would want to take the pre-image because, yeah, that three images of measurable sets are measurable and so on. Yeah, thanks. Okay, so I still have some time. So now we are going to talk about how these topological actions and the measure theoretical actions interact in a sense. So what happens if I have a topological action, a continuous action on a topological space, and I want to turn it into a measure theoretic action? So what I'm asking then is there a measure on X which is invariant under the action so that I could regard it as a measure preserving action in the center up there. So let's let this be a continuous action. Where X, let's say, is a compact Hausdorff space. Does there exist a Borel probability measure on X that is alpha invariant? So I'm going to write it down again. That means that alpha G of A is equal to of A for all G and G and all measurable sets A and X. Okay, does that happen? Okay, and as a first example, we look at the group being the integers. And in this case, my claim is, yeah, this always happens. There always exists such an alpha invariant measure. How do you prove this? Okay, so what we will do is we take a point, any point, an x, and so we sort of just start with something, and then we see, is this invariant? And it's not going to be invariant. And then we ask, how can we make it more invariant? And then we do that step by step. So you start with some point, and you consider the Dirac measure concentrated on that point. Now that's of course not very invariant because, well, if I take x and I go one step to the right with alpha 1 of x, or I go one step to the left backwards to alpha minus 1 of x, due to alpha invariance, these 3 points need to have the same measure. And they don't right now because my measure is only concentrated on x. So then let's just include these in our measure. So let's say this is mu0, define mu1 to be the sum of the Dirac measures of these 3 points. And then we need to normalize because we want a probability measure. Now this is a little bit more invariant than before, but it's again not invariant because you could do the same thing, right? I could again go to the left and to the right and so on. So the same thing that we just did, just include more and more points from the orbit in our measure. So now inductively we define mu n to be 1 over, let's say 2n plus 1. This is a capital N maybe. I equals minus n to n to alpha I of x. Right, so we take n many steps to the left and many steps to the right. We take the sum of the Dirac measures over these points, and then we normalize. And now we have a sequence of measures that are all probability measures. The problem is this sequence does not have to converge. But this is where we have to use some non-trivial function analysis, so I will probably be a bit vague about this. But so this sequence of measures, so by this I mean this is the set of all radon probability measures. No, just radon measures. Radon measures just being like regular measures in the sense from over there. And now function analysis tells you, to be precise, the Ries representation theorem, that this is the dual space of the Banach space of continuous functions on X. And now there's this important theorem from function analysis called the theorem of Banach-Alaoglu, telling you that the unit ball of the dual space of a Banach space is compact in the weak star topology. And therefore, the sequence has a weak star accumulation point. Let's say mu. And then you show, so now you have a concrete measure, and there's a subsequence of measures from here which converge to this measure in some sense, in this weak star topology. And now you show that mu is actually invariant. Okay, so this is to show that even though all of this seems very, I don't know, concrete, like all of this is topology and you're moving around points and you're moving around sets, but very often function analysis comes in a non-trivial way and makes things much, much easier. So in this case, yeah, you have the sequence and then you know that it has a... Yes, that's a very good point, actually. And that's exactly why you need X to be compact. So this does not work if X is just locally compact. Because now what happens is, okay, and a probability measure. Because, yeah, if you look at the measure of all of the space, this is going to be the limit of whatever subsequence you had here, which is equal to 1. And that's why you need your space to be compact, because if X is just locally compact, you can't do this. Right, so much about that. I have 5 more minutes. Now the question is, was that just a coincidence? So we proved this for the integers. Does this hold more generally? And the answer is yes, to some extent. It holds exactly, but it holds when the group is amenable. So theorem, the following are equivalent. G is amenable. And every continuous action of G on a non-empty compact Hausdorff space admits an invariant regular probability measure. Amenability, maybe I'll just write down the definition. This means that, well, there's like a million equivalent formulations of this, but one of them would be that there exists a G invariant finitely additive probability measure. G. Right, so amenability is this very important property that appears in a number of places in mathematics. The most famous one probably being the Banach-Tarski paradox. And it turns out that if your group is amenable, if and only if every continuous action of the group admits an invariant measure. That being said, there can be actions of non-amenable groups which admit invariant measures, but just the fact that every action admits a measure is equivalent to this. And I think that's it. Thanks.
Thank you for this nice talk. Are there some questions?
So I have 2 questions.
Remarks. So the first remark, maybe I think what is true is that amenability is equivalent to the fact that there's a Banach-Tarski paradox for G.
Yeah, there's these sort of paradoxical decompositions, yes. Right? Yeah.
And second question, this in the proof above, does it rely on the axiom of choice?
With like the connected product, which is slightly weaker than the axiom choice. Yeah. Mm-hmm.
Right. Okay. Thanks.
Just a small remark. I mean, you put regular in condition 2, but regularity is automatic for Borel measures on compact spaces, right?
Just any compact space, or do you need anything like countability?
Yeah, sure. But compact Hausdorff, I guess.
Compact Hausdorff is enough?
I think.
Okay.
I think. Mm-hmm.
Thanks.
More questions?
Maybe I can ask one. So I'm not an expert here, but so in this definition, so when an action is ergodic, so what you said is that if your action kind of can give you any point in a certain space, then either this has to be everything or nothing. So to me, this sounds a little bit like a transitive action, but not exactly, right? So, but how does transitivity enter this picture?
So I think transitivity, as far as I know it, is a property of a topological dynamical system or a continuous action, right? Where you would ask that there exists a point whose orbit is dense. That's at least the formulation I know. I don't know. Is that the one you're referring to?
Yeah, something like that the orbits that span everything are dense.
Right. But I think that's an important distinction, because for transitivity, you would ask for the existence of a point that whose orbit is dense. Whereas this ergodicity in the topological context would correspond to a property that's called minimality, where you ask that the orbit of every point is dense. So like that's the difference in quantifiers somehow. Like here it's, so all of this is in the topological context, but the difference is somehow, do you ask there is one point whose orbit is dense, or do you have, so you could have the situation that you have an invariant subset, but still somewhere else there's some point whose orbit is dense. Yeah. Thank you.
I see. And then as far as I know, the transitive actions are interesting because if you look at the transitive and free actions, then the quotients or like the orbit spaces, they will give you like nice quotients, right? So you have something like the orbit space is like in the manifolds setup will give you a smooth submanifold, right? Or the quotient is a manifold if your action is free and transitive, right? Can you say something about the orbit spaces of these? Are they also nice somehow?
So first of all, I'm not super sure about this. This is really enough if you have because I could think of a free and transitive action on a topological space whose quotient is not even Hausdorff. So like just the irrational
disconnectedness.
Okay. So some topological condition also. Yeah, that makes sense. I guess what does quotient mean in this setup somehow, like this measurable setting where, I mean, you don't really, in the measurable setting, everything is just defined up to like null sets, and right, if you just take one orbit, then that typically will have measure zero. So I'm not sure if you can do anything like that in this. Yeah, I think. Thanks.
More questions? Maybe from the audience? If not, let's take the speaker.